Welcome to another video for Stat 212. In this video, we're going to look at confidence intervals for proportions. So as a reminder, what we looked at before was confidence intervals for the mean, the population mean. So that would be in the context of kind of a numeric variable where we have actual measurements or counts or something like that, and we can calculate a mean. However, we also are going to commonly work with binary data, or at least categorical data, where we have maybe two responses of interest. And we'd like to know what proportion of responses fit a particular case, fit a particular condition. And so what we're going to do in that case is try to estimate the proportion of the population that has that criteria, that meets that condition. So I need to actually switch to this. Okay, so that's kind of the big picture here. And there's two changes that go into place here. There's a lot of similarity in terms of what we're doing with confidence intervals here, but there's two changes that we're going to highlight here when working with proportions. The first change is when it's appropriate to assume the normality condition. When is it appropriate to assume that sample proportions are going to be normally distributed around the true parameter? So with means, we talked about that if our variable is already normally distributed or close to it, that's great. If not, then the central limit theorem tells us that if our sample size is large enough, the distribution of possible sample means will still be normally distributed, even if the population itself that it comes from isn't normally distributed. So that's the case for means. With proportions, it's a little bit different because there isn't such a thing as a normally distributed like population for proportions, because if you think about what that distribution looks like, I just have a bar plot of yeses or nos. So my distribution could either look like, so if I have like yes and no, maybe this is what my population looks like, or maybe my population looks kind of like, this, right? So it doesn't really, that whole normality condition from the beginning is a little bit different because I can't have a normally distributed population if I just have binary data. However, if I think about the distribution of proportions, so even though there exists a true p, there is a true proportion of people who say yes in a particular population, there is a distribution of possible p hats that I could get that's going to be normally distributed around whatever that is. So let's say that p is here, and this is going to be my distribution of possible p hats that I could get. So if p is, say, 35%, I could get p hats of 0.32, 0.34, 0.36, 0.31, 0.37, right? They're going to be normally distributed around that parameter. So there is a normality condition going on here. We just have to frame it a little bit differently because it's not going to be exactly the same kind of setup as it was for a numeric variable working with means. So to kind of demonstrate how this works, I'm going to pull up this sim called Plinko probability. So this sim can kind of help us visualize what's going on when we're working with proportions. So what we can do here is we can set a particular parameter. We can set a population proportion here. So we can set it to 50%, 40%, 75%, whatever we want. We could even go to 0 or 1. But let's just go ahead and set it at 55%. I'm also going to, the rows here is going to be kind of like my sample size, like how many people I asked this question to. And I'm going to run one Plinko ball down the pegboard. And this is kind of like sampling 26 people, where if people say yes, it's like it goes to the right. If people say no, it's kind of like if it goes to the left. And where it lands is kind of like my sample proportion here. So in other words, this is kind of like 17 people said yes, 9 people said no. My sample proportion is 17 over 26 in that case. And I can simulate doing this like a whole bunch of times, and I can see kind of my distribution of possible p hats when I do this. So these are all kind of like a bunch of different samples, a bunch of different p hats that I might get. And you can kind of see that there is a distribution of possible p hats in this context that's going to kind of cluster around where the true p value should be. So if p is 55%, then they should be clustering around whatever the 55% value is. So it's going to be about somewhere around like 14 or 15. yeses is what I would expect to get. But because I have random samples, it's not going to be exactly that number, but it should be kind of clustering around that number. So this is like my sampling distribution for p hat in this context. The larger the sample I take, I'll kind of mention here that the narrower this distribution is going to get, the more it's going to center around wherever p is supposed to be. And notice that this is normally distributed already. I don't have any issues with that, and that is always going to be the case. Well, I say it's normally distributed already. It might be looking a little bit oblique at the moment. It's a little bit kind of unshapely. But if I kept running this over time, you would see kind of that very precise normal distribution shape kind of emerging here. But you can kind of already tell it's favoring that type of shape. The only time that this isn't going to work, in other words, the only time that I can't assume that my distribution of possible sample proportions is normally distributed is if my true proportion is too close to the edge and my sample isn't large enough to compensate. So I'll give you an example of that. Let's say that my true proportion is actually 20%. Let me do a little bit fewer rows so it doesn't take quite so long here. Let's say that I sample 20 people. My true proportion is, let's actually make it a little bit more obvious, like 10%. So what happens if I kind of take a bunch of p hats from this distribution? So I'm asking 20 people recording how many people say yes, asking other 20 people how many times they say yes, and kind of record all these p hats. It's not going to quite be normally distributed because there's going to be a hard floor, or if it was on the other side, it'd be kind of a hard ceiling for how high or low p hat can be. So as a result, I can't quite get a normal distribution of p hats when I'm too close to the floor or too close to the ceiling in this context. So that would be the case where I can't make this normality assumption when using or when trying to do confidence intervals for p. So most of the time this works, but if I am too close to the floor, I'm too close to the edge, then I have a problem and I can't use this parametric method for confidence intervals where I assume a normal distribution for the distribution of p hat. So I'll go ahead and stop it there, and I will switch back to the notes here. So that's what this is all about here. So with sample proportions, the issues that were bounded between 0 and 1. So the way that we're going to phrase this condition is we can use this normality assumption and assume that p hat is normally distributed about p if we have at least 10 successes and 10 failures to ensure that our sample size is large enough with respect to p. In other words, what we mean is that in our individual samples, this is all we have, we want to see that we have at least 10 successes or 10 failures to know that we have enough distance away from the edge of 0 and 1. So for example, in those previous examples, we were looking at really small sample sizes of like 20 and 26 there. So if I only have 2 out of 20 successes, that doesn't work. I'm probably too close to the edge because the sample size isn't very big and I'm clearly, or like this indicates that maybe I'm kind of near the edge. So if my sample size is large enough, then I'm probably going to be far enough away that I have a precise enough distribution of possible p hats that I can use that normality assumption. So this is our condition that we're going to look at, is does our sample have at least 10 successes and 10 failures to ensure that we are probably far enough away from those edges and can say that the distribution of possible p hats is likely going to be normally distributed. So that's what we'll do there. Despite, this is change number 2, despite still having to estimate sigma using S, we can actually create a z-interval when working with proportions. Although there is a little bit of an approximation error, it's just that it's going to be pretty small, and software will often take care of that for us if we're using a program like R. It can also deal with that as well. And this is where it gets a little bit weird. When we're working with proportions, we're just going to calculate a z-interval. We don't have to worry about t corrections. We don't have to worry about t distributions. The amount of error when working with an approximated standard error for p hat is rather small, and it's easy to correct for because the sigma to S conversion we're working with proportions, sigma is always bounded between 0 and 0.5. We often don't have a lot of error using S as an estimate. It's going to be pretty close. What was I going to say? That error correction, usually what happens is software will just like slightly estimate our S value up. And there's kind of some corrections that are commonly kind of baked into software calculations to work with that. So we just aren't going to get into t intervals. We're not going to get into the mathematics of the error correction here. We're just going to be using a z interval without worrying about this when we work with proportions. So we're back to our standard z values like 1.65, 1.96, 2.33 when working with 90, 95, 98% confidence intervals for p. So same old formula, except that we're plugging in a p hat for x bar. So p hat's our point estimate, trying to estimate where p would be.